Hey everyone, welcome back for another discussion about machine learning at scale. We are talking about Intel's One API and how Intel is working with Google. It's a fascinating topic, and I'm so lucky to have AG Ramesh, Principal Engineer of Deep Learning Software at Intel. AG, it's great to have you here.
Thank you, Alex. Nice to be here.
You know, this is a 15-minute talk, and so people get your questions in. We love to have AG answer them for you. So I want to just get started and let's just set the groundwork for what we're talking about today. You know, you work pretty closely with Intel. With Intel on One API. Can you tell us about the work you're doing with Google? Maybe just give us an overview of what that is.
Yeah, I'd be glad to, Alex. So as you know, One API is a way that you can access some of the Intel hardware and be able to exploit some of the capabilities in terms of the instruction set that it offers to accelerate AI and machine learning software. So as my role, I lead a team that works very closely with Google. So we take TensorFlow. As you know, TensorFlow is one of the most popular frameworks being used by people and data scientists all over the world. So we work closely with Google and integrate One API, and specifically there's a component in One API that's One DNN. It includes a bunch of primitives that can accelerate and run machine learning algorithms on Intel hardware. So we work with Google and make sure these are tightly integrated into TensorFlow. So when customers, who are deploying solutions on Intel hardware, they want to get the best benefit for their machine learning applications and workloads, they'll be able to using just TensorFlow. They're all used to using TensorFlow. They're very familiar with that, and it's just getting setting the right settings for the Intel hardware, and you get all the benefits from the hardware, underlying hardware, without having to understand. The user doesn't need to understand what system they're working on. Is it a Skylake platform, or is it Cascade Lake? They don't need to worry anything about all those is handled by the One API libraries.
So how are you optimizing TensorFlow? And for those who may not be familiar with it, TensorFlow is an end-to-end open source platform for machine learning. It has a comprehensive, flexible, ecosystem of tools, libraries, and community resources that lets the researchers to, push then these state-of-the-art and ML and developers to easily build and deploy these ML-powered applications. And so how is Intel optimizing TensorFlow, and what are some of the results of it that we would recognize in the market?
Yes. So TensorFlow has, supports multiple backends, right? So you can run it on an NVIDIA GPU. You can run it on, an Intel CPU, or even, recently you can run it on ARM CPUs also. So it has a backend that can be customized, for the specific hardware. So that's the code that we, go and tweak or enhance and have those the kernels, what we call the execution kernels, call into One DNN. So we add the necessary code to marshal the data between what TensorFlow uses and what's expected by One DNN for that specific platform, and we write the code that handles the passing of data from TensorFlow to One DNN, and then One DNN executes the instructions and gets the data back. So we've seen some very good results. So we worked with one of Google's applications. This is a deep variant application that does gene sequencing, and we were able to, with some of these optimizations, we were able to take a workload that ran for about 11 hours and on a Skylake platform, and we will bring that down to about 3 hours. So it's more than 3x improvement in performance by using some of the optimizations that we do.
What is that offering then the people who are building out the models or building out, these workflows when you can reduce the time like that? I mean, we all know that, speed is is what changes software, and often it changes software because there's less risk, really. Is it a matter of, allowing then just them, the engineers at Google to try more?
Yeah, and as you probably know, models are getting more complex. We've in the last 5 years we've seen the complexity of models probably increase by several thousand times. As a model gets more computing intensive, right? They need more hardware support. So all these optimizations enables us to write models that are more sophisticated. The more the models are sophisticated, the more accurate they are for many of our use cases. So that it basically enables the data scientists to use more complicated models on essentially widely available hardware like the Intel platform.
So it allows them to use those more the complicated models. And what are some of those models? I mean, I know there's a few that you've talked to me a little bit about.
Yeah, I think there's some common models that are very popular these days. For vision we have the standard ResNet models that does classification, and also we've spent a lot of time recently optimizing BERT. So BERT is a model from Google. It's used for a lot of the natural language processing tasks. So we've been kind of working to more update TensorFlow so you can do inferencing and also what we call fine tuning and of BERT. So you can run all these algorithms now on Intel on Intel hardware or Intel CPUs right now. And yeah, BERT is one of the most complicated models that is available, right now.
So BERT is for natural language processing, correct? So
yes.
So Google Cloud would use that, I guess, or you'd see that on Google Search. I think it was originally developed for Google Search, wasn't it?
Yes, it was originally developed by Google. Yes, for their search and internal applications. Yeah.
So you're really helping optimize these frameworks then. And so then by doing that, the frameworks just can be easier to be used for the developers. How are the developers contributing back to these, to your work to make it, to optimize it in itself?
Yeah, I think we work very closely with, our customers and our partners. So we get, constant feedback on how they use the models and where they'd like to see a lot of improvement. We talk to several customers who are writing unique models that are different from some of the standard models like ResNet and BERT. So there are some unique characteristics in those models that we use that to improve TensorFlow even further in terms of what it can do, and then the performance that you can get from running those on Intel CPUs and GPUs.
We have one question from Bruce Gain, and Bruce is a reporter for the New Stack, a correspondent for us. And Bruce has a question: how has the role of the API changed and evolved for TensorFlow and machine learning in general? So how has the role of the API changed for TensorFlow?
Yeah, I think for the TensorFlow, it's one API has made it a lot easier for us. So, for example, then TensorFlow was mainly, most of the inferencing and training was done on floating point 32, which is a 32-bit floating point format that's most popular for training. But we've seen and we've had some hardware enhancements on the Intel platforms that can accelerate lower precision inference using 8 bits and also using bfloat, which is a 16-bit format, to do faster training and inference. So using one API has enabled us to get these new formats into TensorFlow much quicker, because the one API kind of hides a lot of the abstractions that you need, hides lots of the arithmetic behind the computations for some of these low precision. It hides those abstractions and removes those from TensorFlow. So we've been able to, with the help of these APIs, and we've been able to integrate and bring these opportunities or bring these changes into TensorFlow much easier. For example, we were working with Google last year to add, bfloat 16 support. It probably, maybe took us a couple of months, 4 to 6 months or less than 6 months to enable that support, so that it could be used on, on the Intel platform that was coming out last year that supported bfloat 16. And the API keeps, evolving. So right now we just released a preview of the API, which can do more than what the previous APIs did. For example, the one API, one DNN solution just worked at kernel levels. So now we have a graph API which looks at the entire graph, not just at the kernel, at a single convolution. It looks at the entire graph and tries to optimize and run the entire graph rather than optimizing one single kernel. So we're also constantly evolving the one API to meet the growing demands of AI.
How is that meeting the demands then? How is that meeting expected demands by optimizing the graph? And maybe you could explain what you mean by optimizing the graph.
Yeah, I think so. So what? So basically, as deep learning is built using various operators like convolutions and matmulls. Each of these layers are interconnected. So if you know the connection between the various layers, you can do a better job of optimizing the whole workload. Right? It's still, so optimizing each individual piece, only gives you this much because you don't have a visibility of how it's being used. And so when you have the whole graph, we can make some trade-off in optimizations to make things much faster at a whole. It's like when you put 2 and 2, it's better than 4. So that's what these graph APIs bring you. Right? Being able to see the whole picture and being able to do much better optimizations, because you can see the whole picture.
So just in conclusion, what's the direction that you see one API taking with Google, and how does that reflect the rest of the market?
Yeah, I think we are actively working on supporting multiple platforms. Right now, most of the work that we've done is on Intel CPUs. So one API now works on the Intel GPUs. So we are now extending some of the work that we did with Google to handle the Intel GPUs. So we are building those APIs that will allow us to access one API, from TensorFlow through these APIs. So we, and then we want to do this in a seamless way. So, so what we have called it XT strategy. We want to be able, the customers to just write, their models or for just one platform, and be able to let, the one API handle how it gets executed. So you may, some operators may be easy to run on a CPU, versus an Intel GPU. So that's kind of, partitioning and things can be handled inside one API. So we're kind of working, to get all these APIs into TensorFlow. So it'll allow us to do these optimizations in future.
Well, AG, thank you so much for taking the time to talk with me about how you're working with Google through one API. AG Ramesh is Principal Engineer of Deep Learning Software at Intel. AG, thanks so much for joining us.
Thank you, Alex. Thanks. Nice talking to you.